Good afternoon, friends. So today we are going to discuss on remote sensing and geographic information system for hydrocarbon exploration. And I am Dr. R.S. Chatterjee from Geosciences and GIS Department of Indian Institute of Remote Sensing. So we have almost 1.5 hours. So we'll try to finish it by 1 hour or so that we can have sufficient time for interaction. Okay, so let us start. Remote sensing and GIS for hydrocarbon exploration. So what is a hydrocarbon? Hydrocarbon is basically it is a compound made of hydrogen and carbon, isn't it? And there are economically important hydrocarbons. They include like fossil fuels such as coal, petroleum, and natural gas. And many of their derivatives such as plastics, paraffin, waxes, and solvents and oils. So again, hydrocarbons along with nitrogen oxides and in addition to sunlight, they contribute to the formation of tropospheric ozone and greenhouse gases. So this is not very your environment friendly. But anyway, so we need to know what are the different types of hydrocarbons now. So hydrocarbons basically hydrogen and carbon, and this is maybe a chain, maybe rings as well. And there may be different kind of hybridization like sp3, sp2 and sp. Okay, so now depending on the number of carbon atoms involved in the chain, so there are 3 types of hydrocarbons. First is like up to 4 number of carbons like CH4, C2H6, C3H8 like this up to butane. So they are basically gases and they boil in this temperature. Okay. And when the chains are a little longer, like even up to C18, then they are liquids at room temperature. And when the chains are very, very long, like it is beyond C19, so more than 19 carbons involved in the chain, then they are solids at room temperature. Okay, so what is important to us is hydrocarbons, naturally occurring hydrocarbons. They are like coal, petroleum, and natural gas. Okay. Now, if you see the statistics of energy usage, particularly of commercial fuels, that we can see this is the world energy used by fuel. Here, what we see in case of Asia Pacific, there is the fuels like coal is this, so maximum we use coal in the Asia and Pacific region, and then followed by oil and natural gas. But if you see in the US, there is oil is first, then oil, then natural gas, then coal. And if you go to the Europe again, this oil and natural gas is more, followed by coal. And this is like other South Central America and Africa. This is something like this. This is your 1 million tons of equivalent, oil equivalent. Okay. So now this the energy metrics in India. If you see, this is 2009 statistics. What we see, it is mostly around 97% is your fossil fuels. Okay, so fossil fuels like your petroleum, natural gas, and coal, this is the major portion. All of us know that. And if we project it for 2035 for the world energy usage, even then also we see it is almost 80% is the fossil fuels. So hydrocarbons, naturally occurring hydrocarbons. So this prospecting and exploration of hydrocarbons is very, very important for us for energy. Fulfill the energy requirement globally as well as for the country. And remote sensing plays an important role. Remote sensing and GIS that plays an important role in this. There are many steps in this exploration strategy. Remote sensing and GIS that constitutes one component. This is the reconnaissance survey we can do with the remote sensing. But in GIS architecture, then we can include a number of other information that I will explain later. So number of other this information like from drilling data, like seismic data, like other geophysical data, as well as this remote sensing data and existing geological data. And all this data together we can visualize together, we can analyze together, and we can integrate together. And based on that, we can make some exploration strategy for a particular area. First thing is targeting hydrocarbon in a particular area, and followed by what kind of exploration can be done in that particular area. So to begin here, these hydrocarbons, this is the coal. This is the composition of coal mostly. So you can see it is a very long chain hydrocarbon. So this is hydrogen rich lateral chains, And if you see the remote sensing properties of coal, so it is a black, almost it is like a black body. and here the reflection is very, very less. What we see in case of this panchromatic range, mostly in 0.5 to 0.8 micrometer, see only there is 10% reflectance, only 10%. And if you see the thermal properties, then coal occurs as a seam. It is a bedded deposit geologically, so it occurs as coal seams. The coal seams it may be a deep seam, it may be a shallow seam, or sometimes it may be exposed as well. So in case of deep seams, what is the thermal characteristic is that here the geothermal gradient is little more than the natural, the normal geothermal gradient. It is around 1 to 2 degree centigrade more. But in case of shallow seams, what happens? Shallow coal seams, when it occurs, it is a little reasonably when it is closed in terms of thermodynamically, when it is a closed system, then there is a chance of spontaneous combustion. It can catch fire. So that is one kind of hazard. So coal fire can take place spontaneously. This is in case of shallow seam. And in case of exposed seam, what happens? Because it is black in color and it is very close to black body in terms of emissivity. So it absorbs a lot of the solar energy, and as well as it radiates a lot of solar energy because its emissivity is very close to 1, around 0.99 or so. So this is all about the coal, but mostly we'll focus on the petroleum and natural gases for remote sensing and GIS related studies, as well as we will also see, if time permits, for some of these unconventional hydrocarbons, how to use the remote sensing and this other input together to assess this occurrence of these unconventional hydrocarbons and basically targeting as well as quantification of these unconventional hydrocarbons. Now, see, in case of petroleum and natural gas, there are many advantages. So these are the summary. You can see this is widely available. It's simple combustion process that can directly heat and generate electricity. So very convenient for usage, easily distributed, and good infrastructure in place in all over the country. And they have high energy content, but they have many disadvantages as well because it is non-renewable. So we need to be very careful. So that is why nowadays it is more focused on the unconventional or non-conventional hydrocarbons because there is a large resource of non-conventional hydrocarbons. So this is one of the disadvantages. Then air pollution, including greenhouse gases, and there are other economic things are there like price instability. Then it is import and also there is environmental impact. That is one of the major disadvantage. So now we see this for petroleum and particularly if you talk about hydrocarbons in general, we see that hydrocarbons in general, they have IR absorption peaks around 2800 to 3300 centimeter inverse, which is the wave number. So that comes around 3.5 to 3.0 micrometer. 3571 to 3030 nanometer. So this is the range where there is a absorption peak in naturally occurring hydrocarbons. Hydrocarbons in general. This is due to carbon-hydrogen stretching vibrations. But this stretching vibration is in case of steeper bonds, like in case of sp hybridization. Okay, so that is shifting towards your 3030. That means 3 micrometer. And in case of this your sp3, that means methane, butane, this kind of hydrocarbons, it is around 3.5. So where it is more number of bonds between carbon and hydrogen, it is shifting towards the shorter wavelength 3.0. This is basically in the middle infrared. Okay, so thermal region. But if you talk about this visible near infrared or short wave infrared region, then this Clutis showed that there is hydrocarbon bearing substance have characteristic absorption peaks around 1.73 2.31 micrometer, or 1730 to 2310 nanometer. Okay, so if we can use that absorption peak in the visible infrared VNIR region, visible near infrared region, that we can explore these hydrocarbons. This is onshore exploration can be done, onshore petroleum exploration can be done. So based on this absorption peak particularly, but we can use even this thermal as a peak. So detection of onshore hydrocarbon seepages is very, very important. We can detect, if we can detect this onshore hydrocarbon seepage, then we can explore, we can target where petroleum occurs. Okay, detection of oil and gas contaminated soil. Sometimes what happens, oil and gas, you may not get pure also, but it contaminates the soil during seepage. And it contaminates with soil and sand. So the soil and sand which is contaminated with oil and gas, they will have a different kind of signature than the pure sand and soil what signature you will get. So the contaminated one will have different signature. Now detection of vegetation stress also, sometimes where there is seepage of oil and gas is taking place because of the contaminated soil, these vegetation can also be detected, and based on these kind of criteria, we can identify some of the areas there may be oil and gas underneath. So, but it is not possible everywhere. Only where this oil and gas is seepage is taking place to the surface, there only we can do that. Where the oil and gas works underneath, and there is no seepage to the surface is taking place, we cannot do. So we need to go for some indirect evidences so that we can target hydrocarbon underneath. Okay, so we'll discuss later on. Now, where this it is this oil and gas this is coming out to the surface, there this hydrocarbon can be detected either in the form of direct signature or contaminated soil signature. So here this when 2004 he has developed an index like mineral index, like snow index, different kind of indices he have already you know. So there is an hydrocarbon index he proposed. So the HI or hydrocarbon index, that is basically it is focused on the 1.73 micrometer. That what I told you, that visible in our region there is all one absorption peak. So if you see here, there are the these spectral plots of this your this sand, uncontaminated sand. This is contaminated sand. This is the green vegetation. There is some other things like plastic. So there are 4 spectral plots are there. So these two are very, very important. These two. One is uncontaminated sand and another is contaminated sand. If we compare these two spectral plot, then what we see, in case of uncontaminated, you see this is a smooth curve. But in case of contaminated, oil contaminated sand, what we see, there is some feature we observe. There is an absorption peak here around 1.73 and there is another absorption peak here around 2.3. So what they have addressed with this one, this index what they have developed using this particular absorption peak. So if we see this extended view or zoom of this, it will look like this. There is some kind of absorption peak here. Now here if we say this is lambda A, this is 3 point A, B and C. This is based on the this your absorption depth, band absorption depth, this your logic. So here if you see this is point A, this point B and point C, there are 3 points if you consider. This is the wavelength here lambda A, this wavelength here lambda B and lambda C. The index has been formulated, it is something like this. You can see here HI is equal to lambda B minus lambda A, and this RC minus RA divided by lambda C minus lambda A wavelength plus RA minus RB. So lambda A, lambda B, lambda C, these are the wavelengths, whereas RA, RB, RC, these are the reflectance at the corresponding points, corresponding wavelength. Now, if hydrocarbon bearing material is present, that means if the soil or sand contaminated with oil or natural gas, in that case, what happens? This HI value is greater than 0. If there is no hydrocarbon bearing material is there, that means soil or sand is not contaminated with oil or gas. In that case, this HI value is close to 0. Now the question is, this absorption peak, what we are talking about 1.73, that is also very close to strong water absorption peak. So we need to be little careful, and we have to see this whether we are getting some water in this particular area. But in the case of water, absorption peak is much stronger. So this is what is important to note. Now we are coming to the beginning of this your petroleum, this oil and gas, how they are formed. So most of us we know this how this oil and gas form. In the oceanic environment, there are the these sea plants and these animals. When they are died, they are deposited over the seafloor. Then they are buried with the sediments, and after a long time, with the pressure and temperature, high pressure and temperature, they are converted. Okay, they thermally cooked, and from that, this material, organic rich material, is known as kerosene. So with this high temperature and pressure, then they are converted to oil and gas, and this oil and gas then they migrated to some place where it can be accumulated. After it is accumulated at a place, okay, then it needs to be sealed with a cover. Okay, sound is not going properly. Okay, it's fine. So now this oil and gas is accumulated, and now it needs to be, there is a sealing, this is required. So it needs to be covered perfectly so that oil and gas should not come out to the surface. Because if it is not sealed, then what will happen? Because oil and gas, they are very, very volatile, very light. Then what will happen? It will come out to the surface. So that is why sealing is required. So we will discuss those things and how remote sensing can help to prospect, that also we will discuss. Now this is the origin of petroleum. So what we told, that after the this death of the organisms, they are deposited over the seafloor, then they are mixed with the sediments, and they make this kerosene, this organic rich source rock. They are thermally cooked, thermally matured with high pressure and temperature. Okay, after that, what is happening? There is oil and gas is produced. Okay. Now what happens? This type, there are maybe different types of kerosene which produces different kind of petroleum. Like if in kerosene where the algal material is more, then what will happen? It will produce oil. This is oil prone. Whereas if there is wood is more in this material, then what will happen? It will be more. It will be hydrogen poor, and it will produce mostly gas. So this is what we'll get from different kind of kerosene. Now after this, it is thermally cooked or thermally matured, then it is producing oil and gas. Then oil and gas, they are very less dense. And so what will happen? Because in the source rock, there is the pore spaces are there, but they cannot accumulate in high concentration. So what happens? And because they are very less dense, so they migrate upward through this porosity and permeability of the rocks, and then finally they are going up and up. Then they are taking a place where there are a lot of open space is available, where they can accumulate. So these are known as the reservoirs. There are a lot of open spaces available where they can accumulate. Okay. After this accumulation, what you need? It needs to be covered, sealed, so that this oil and gas cannot go out from this storage. So now accumulation of oil and gas in sedimentary and structural traps. So what is the trap? This is the sealing rock. Cap rock is important. So sealing rock, also known as cap rock. So the cap rock, it covers it. This is the reservoir rock. Okay. The reservoir rock, because it is less dense, so here there will be water, and then there will be oil, and then gas is even more volatile. It is very, very light, so it will be occurring here. So this is a structural trap, anticlinal fold. This is basically anticlinal fold. Okay, so gas is occurring here, followed by there is oil, and here there is the water. But this structural trap can also be a fault trap, is also a structural trap. So in this case, what happens? This is faulting is taking place. By the faulting, what happens? It is getting sealed. Okay, this is the reservoir rock locked here by the impermeable rock. So this oil and gas, what is accumulated here, that cannot pass through it, and it cannot come to the surface. So that is the role of the fault. So the fault causes this sealing, confining this oil and gas in the reservoir rock. So here what happens? Here water is occurring, and the oil is occurring. Here the gas is occurring. Sometimes what happens? There is structure, geological structure may not be there. So even then, oil and gas can be accumulated in a reservoir rock like this. This is the dipping beds, you can see, and this is reservoir rock. Means there are a lot of porosity and permeability in this rock. So water, this oil and gas can be accumulated well on the source rock. It has migrated to the reservoir rock, and here at the beginning there is water, then followed by their oil and then gas. But what happens here? The cap rock, you see, cap rock is due to unconformity. So they are material what are deposited over this material is impermeable. So what happens? It acts as a cap rock. Now, where then this oil and gas can occur or petroleum can occur? It is in sediments. So we need to know the sedimentary basins in the country. So this is one sedimentary basin, tectonic of the sedimentary basins. You can see the different areas the sedimentary basins are occurring. Okay, so what is important, that sedimentary basins, but it needs to be the geological age is very, very important. Generally, these sedimentary basins where there are a lot of organic matter was available, okay, and it was buried, then only you will get the hydrocarbons. So in some cases, these hydrocarbons may be coal, and some cases where there is the oceanic environment you are getting, so here you can get the petroleum. So now, here this role of remote sensing, what is our area of interest today? That is the role of remote sensing in petroleum exploration. That is, we will focus more on that. So these elements of petroleum exploration, what? We need to know the source rock. Where is the source rock? Where petroleum can be found. Then after it is the formation, this petroleum like oil and natural gas, it migrates from the source rock to the rock where there are a lot of open space. It's a lot of porosity and permeability, so that this oil and gas can be accumulated in large volume. So this is the reservoir rocks, okay? And after it is accumulated in the reservoir rocks, so what happens? You need to have a cap rock above it, okay? When it is accumulating, so if there is no cap rock, then what will happen? It will go out. So you need to have a cap rock or seals, okay? So this it should be impermeable, okay? So this now this petroleum trap needs to have a particular geometric configuration. If this geometrical configuration you don't get, then it cannot accumulate in a large volume. So that is why some geological structure or some very typical your stratigraphic setup is required. Okay, sedimentary setup is required where this petroleum trap can be developed, where the oil and gas can be accumulated and it can be capped by an impermeable this rock cover. Now this role of remote sensing, what are the inputs required from and what the remote sensing can serve, remote sensing can supply in petroleum exploration. It supply or reconnaissance this input, so very detailed information it cannot provide. So what kind of information it can provide? It can first hand information is whether it is a sedimentary basin or not. You need to know first. So because you go for petroleum exploration in an igneous rocks, there you will not get it, isn't it? So first identification of sedimentary basin, whether the area is in a sedimentary basin or not. First, then if it is sedimentary basin, then what kind of rocks are there? So lithological discrimination or rock type identification is important. And then what are the geomorphology, terrain is important, because from the geomorphology or from the terrain, particularly from the geomorphological anomalies or terrain anomalies, you can decipher or you can interpret that there are some geological structure underneath, okay? So this geological structure supports the accumulation of oil and gas. So for that purpose, geomorphology is very, very important, okay? And geological structure and tectonic information is important because particularly the traps, these petroleum traps are mostly in the structural traps, okay? So that is why the understanding the geological structure or tectonic information is very, very important. Now, the first information is for criteria for discriminating rock types that I covered previously in this basic lecture on geology and geomorphology, remote sensing for geosciences or remote sensing interpretation for geology and geomorphology. Here, how can you identify broadly the rocks, the igneous rock or sedimentary rocks or metamorphic rocks? These are the criteria I have given earlier. So I am repeating again. For sedimentary rocks, what is very, very important? That bedding is very, very important. So presence of bedding, if you see that there are bedding is available in the rock, so you can say that is a sedimentary rock. So this bedding gives layered appearance in the satellite image or aerial photographs. This layered appearance we get sometimes in igneous rock, particularly in extrusive igneous rock. So we need to be a little careful. Okay, it should not be this volcanic layering. So if the layered appearance we see, so generally we can identify that this is a sedimentary terrain. And in case of sedimentary rocks, these rocks are very soft. As they are very soft, so they are very prone to weathering and erosion. So that they will give you a lot of dissection in the rocks. Okay, and will be a resistance. In the hard rock will be resistant, that will produce some kind of ridge. It's some problem. So, okay, let us start again after interrupting. So then for sedimentary terrain, so these are this layered appearance, then this dissection, then their differential resistance. It gives you this typical geomorphology or landforms, ridge valley topography for in case of alternate hard and soft rocks, and there are characteristic landforms, okay, for horizontally bedded rocks and for dipping beds like Cuesta, Backs, Mesa, Butte, like this. So those things we have discussed previously, so we will not spend much time here. So this is just to recapitulate once again. This is how sedimentary looks like. So you can see here, these are aerial plots. You can see how the layered appearance are so clear, and this is the ridge and valley topography is also very, very clear. So from that you can interpret this is a sedimentary terrain, and rocks are mostly sandstone and shale. Like here also there are the layered appearance, and you can see here there are two kinds of rocks. Here the rocks are little coarser, and here the rocks are finer because the drainage is very, very broad here, and here the drainage density is very, very high. So here underneath the alluvium, the rocks is perhaps shale, and whereas here this is the sandstone, and in some cases there are conglomerate as well. You can see here some faults as well, cross faults ridges. Okay, so but sometimes what happens, you can see the folds also. So in the sedimentary terrain, when it is deformed, and this exposed folds can be very easily identified from remote sensing data. So that we have discussed earlier. So when the folds are exposed, you can interpret well, because from the curvature of the beds, from the change in the strike and tip of the beds, you can interpret that this is a folded form. And what the geometry of the fold, that for that you need to know how the strike is varying and how the deep of the folded layer is varying. For that we need help of the flat iron. How the flat iron means, flat iron tells about this direction of dip, as well as the relatively or qualitative this magnitude, whether it is high steeply dipping, moderate dipping, or shallow dipping beds, so that we can interpret here. Like here the dip is little less gentle dipping, whereas here the dip is increasing, and here the dip is almost very steep, almost vertical, subvertical. And from that you can infer, or you can decipher the geometry of the folds. It is mostly anticlinal fold, and it generates very close to a dome. Okay. Now, when it is this fold does not show this curvature, this folded nose is not seen. Sometimes also you can interpret there is a fold from the symmetrical repetition of the beds and from the dip of the folded layers on either side. For example, here you can see the symmetrical repetition of beds. This is the northeast, the Tipom, Hubon, and the formations are there. So you can see here the beds are dipping here towards this direction, towards the center, and here the beds are dipping towards the center. So here basically it is a synclinal or synformal fold. And when this nose is clear, then that is very easy for us to interpret that it is this plunging fold. Plunging fold, for example, this is a plunging fold, but from the tip of the beds we can interpret that this is a plunging anticline. But these are only in case when the folds are exposed to the surface. But for petroleum exploration, what is important is folds will not be exposed to the surface. It will be underneath, buried folds, and it will be covered by the capons. So for that, we need to interpret folds either from the topography or from the drainage or a number of other evidences. Indirectly, we need to interpret that there are some geological structure underneath. For example, in this schematic diagram, if you see, the fold is, because there is an anticlinal fold, here it is symmetric, here it is a little, it is not symmetric, asymmetric folds, but what it gives you subtle topographic relief. So, find out subtle topographic relief. What we need? We need a digital elevation model, we need a topography, high resolution topography, high quality topography. So, we need to have a very high quality DEM. From that, we can draw some profiles and we can see whether there is a subtle topographic relief can be observed in some areas of doubtful area where petroleum can be there. So if you can interpret there are some folded structure underneath, so then we can say that where this petroleum can be accumulated. So this is a syncline, this is second order topography, so I'm not going to discuss here now. So now from the drainage also you can say the folded forms. buried faults can be interpreted. Here, for example, this adjacent drainage, you see one case it is a radial one, and in another case it is a concentric one. So when you see both the drainage side by side, okay, then what happens? Then it means that there is an anticline and syncline side by side. It may be so. But if you say only radial drainage only, then there may be a dome, there may be some intrusive, there may be anything, but it can also tell that there may be a dome also, domal structure. And domal structure is very important for petroleum exploration. Now, this is another kind of indirect evidence. This is the width by depth ratio of the stream. We see the width and depth ratio, then we can see that when it is cutting, when the width by depth ratio decreasing, okay, so that probably it is cutting a geological structure, maybe a fold like this. Here if the stream was normal width and depth ratio, but when it is cutting this fold, what will happen? Becomes deep, and this width will be very, very narrow. So width by depth ratio will be very, very less. Again, after this crossing, then it will become normal. So from that we can interpret there may be a fold here and underneath, and subsurface fold rather, buried fold. So that is very, very important for petroleum exploration. Again, from the meandering also, sometimes we can interpret there may be a fold, like if there is in one place, there is a compression, that means there is a some this topographic gradient is reduced substantially or abruptly. So how it can happen? If there is a folded structure underneath, if there is a buried fold here, then that produces a topographic gradient against that. Then what will happen? The drainage will show the compressed meandering. So this is one kind of evidence. This is the diagram, but we will see a number of satellite images also and some real case example. Okay, so now we see in this case, this is double drainage deflection. Some tells you that there may be a buried fold underneath, that buried anticline. And what is interestingly very interesting here, you see here the parallel drainage deflection. If two drainage are deflected at the same way, the same pattern, it is also deflecting like this, it is also deflecting like this. Then it is also coming like this, it is also coming like this. So that can happen when there is a folded structure underneath. But it needs an acute angle to cut the folded structure. That's why both are making this angle. Okay. Again, after it is crossed, then again it is becoming like this. Okay. It makes an obtuse angle with that. Okay. So this indicates there may be a subsurface fold underneath. And now to interpret fault or to identify fault, what we need to see in the satellite image, we need to see that there are offset in the beds or offset in the ridges. Like here you can see the offset of the ridges. Okay, so based on the offset of the ridges, you can interpret there is a fault here. You can see here also there is a fault here. But there are some of these linear features are only lineaments. They are not faults. Some are faults where there is the displacement of the ridges is visible. Displacement of the beds can be seen. And in the lineaments there can be fracture, there can be joints as well. Fractures are irregular in pattern. They are relatively long. Whereas joints, if you see, they are very systematic pattern. This is parallel. Again, this set is parallel. So these joints have a systematic pattern, whereas fractures has this random, irregular pattern. And faults when it is a lineament but with displacement. Now here, from the drainage anomaly or from the land use land cover, you see the land cover it is curving like this. And also the drainage, it was a normal meandering, but here suddenly it got straight. So that says that there is a possibly there is a fault, and yes, there is a fault here, and you can see these beds underneath this vegetation has been bent here. Why it is bent? Because of displacement towards this, and this is displacing towards this. Although there is a rupture has not taken place. Okay, so so this is basically a ductile. You can say this is a ductile shear. So there is offset as such has not taken place, but in remote sensing terms we call it a fault. Okay. So this fault, identification of fault is also very important to for petroleum exploration, because in some of the cases petroleum is accumulated and it is sealed or capped with by the process of faulting. Okay, like here it is. If we see this example here, that is anticlinal one. So here oil is accumulated because of the anticlinal structure. Because when there is anticlinal structure, there are open spaces between the beds. We have some open space between the two beds, adjacent beds. So in the open space, there are this oil and gas can be accumulated. In fact, this is a reservoir rock, which is lot of porosity and permeability. So here there is water, here there is the oil here, but there are some open space as well as reservoir rock where and oil can be accumulated. Now here, what happens due to the faulting? There is the here as in anticlinal case, you can see this is the cap rock, so it does not allow oil and gas to go through it. But in this case, this capping has been taken place by faulting, because rock is this one, and these are the reservoir rock where this oil and gas has been accumulated. So now in this site, this oil and gas has gone out. This could not be sealed because of the geometry of the beds, but here the bed is dipping towards this, so oil and gas, because they are lighter, so it is accumulated here. As it is accumulated here in this area, so when there is faulting taken place, and this is the impermeable bed, it is covering above the permeable bed, so what happens, it cannot go through this. So it is entirely covered. So then oil and gas cannot go through it. And in this case, what happens, it is a sedimentary or stratigraphic trap. It is happened due to the persistence. So this is here the rock is permeable and porous, whereas here due to persistence, this rock is impermeable. So what happens is petroleum accumulates here, this is the oil and gas, and this is the water, and here this rock is impermeable, so it does not allow oil and gas to go through it, and it remains here. So if you make a well here, drill a well here, and you can this extract water, oil and gas from here. Okay. Now this is the petroleum traps. Some more examples you can see: folding followed by faulting, causing this capping, and this oil and gas accumulated. One in case of this folding trap, and this is a faulting trap. It's basically a combination trap. Folding and faulting both are involved. This is basically a stratigraphic trap, although it shows some kind of folding. It is a dipping beds with some curvature, but it is covered by this sediments are impermeable. Basically, it is an unconformity, and that causes the capping of the petroleum. You see here the petroleum accumulated here, and it cannot go out because of this overlying rock, which is impermeable. Similar kind of example here, this is a folding followed by faulting. So this is the trap, and here this is salt dome, and associated folding and faulting that gives you the accumulation of oil and trapping, capping of the oil and gas. So these are the possible areas of the exploration for petroleum. So this, if you see in the satellite image, you can see here in the northeast, it is a lot of potential for oil and gas in this area. So what are the areas in this region? What are the areas which is should be targeted for oil and gas? For that, we need to interpret the satellite image, and we can see this is the series of folds. This is anticline and syncline. You can see here in the Mizoram area. This is the Assam. This is Silchar area. Okay, and in the next example, I'll show you near Silchar, the Barak River. It shows a very typical drainage anomaly. Okay, so this is the area where oil and gas can be accumulated. So folds, faults, you can interpret from there. There are the thrust, so many geological structure we can interpret, and this is the geological structure which is buried underneath, and there is impermeable rock above it. So those are the areas, the potential areas of oil and gas accumulation, and we can explore this oil and gas from such areas. And you can see one such area. This ONGC has explored from there. This is source is also from the ONGC. So you can see here from the satellite image, this the drainage shows a anomaly, isn't it? So drainage meandering, it is meandering taking place. The meandering is a little more, as well as the meandered river. It shows a circular pattern, circular anomaly. So why this kind of this drainage anomaly we observe? In addition to the previous drainage, you can see these are the previous paleo channel. This is the Oxbow lakes, and you can see. So a lot of geological structural disturbance you can interpret from here. So actually there is it. So when we see the subsurface, so we see the subsurfology. What we see, that is the foldal is a folding is there, anticlinal fold, and there are a number of faults crossing through these folds. Okay. Now this is one case example that we have used. In this case, the remote sensing and seismic data together in association with ONGC. So here this is the Kutalam area in the Kaveri Basin. So this is a old study. So here we have interpreted the lineaments, this and faults from the satellite image. So this is the lineaments here, and we have the seismic data also. This seismic time map. Okay, from the seismic time map, we need to do some processing we need to have some borehole data to get this depth of these sediments and the velocity of the seismic wave. Okay, and this is the seismic time map. All together, we can generate digital basement topographic map. Okay, so this is the digital basement topographic map of this area of this. So from this digital basement topographic map or DBTM, or you can say terrain map. Okay, we can interpret these basement structures. Basement structures like folds, like faults. There are some strike slip faults. There are some cross faults and faults are there. Okay, so from this basement structure, we can interpret some of the possible areas where this petroleum, this oil and gas, these potential areas of oil and gas. Okay. Now, when we compare these surface structures, so this is the surface lineaments, Rose diagram, and this is the basement faults, what we have interpreted from the seismic data. So from the seismic data we get, this is the vector mean, okay, one vector mean, but from the surface data we get two vector mean. So there are two sets of lineaments we observe. Now we need to very carefully, we need to see the areas where this vector mean, basement faults vector mean is very much matching with the surface lineaments vector mean. If it so happen, what does it mean? It means that the basement faults are propagated to the surface and there is a consistency from the basement faults to the surface. So if there is a these faults are consistently propagating to the surface, then what will happen? Although you have sufficient petroleum accumulated underneath in the this reservoir, but because these fractures are continuous from the basement, then what will happen? This will act as avenues. And then this petroleum will come out from the reservoir. And so although there are a lot of potential for this petroleum and petroleum accumulated actually there, but because of your continuous fractures from the basement, these act as the avenues, so the oil and gas will come out and you will not get anything there. Okay, so this we need to be careful there. So this kind of studies are important. So based on all this information from the remote sensing as well as from the geological structure interpreted from the seismic data. So remote sensing and seismic data together we interpreted and we have identified some of these favorable zones, favorable zone 1, favorable zone 2 and favorable zone 3. So there are a lot of scope to refine the study. So now when the oil or petroleum is occurring in the offshore area, petroleum exploration is underneath this. So what happens? This oil and gas, it can come out and there can be seepage and it can produce the oil slicks. And if the oil slicks are natural, so oil slicks can be two kinds of oil slicks can be there. Okay, one is natural due to natural seepage. So if the oil slicks develop due to natural seepage, then what does it mean? That means this underneath in the seafloor there are the areas where you can find the petroleum. So this is the area where petroleum resources can be prospected. Okay, but if the oil slick is a little thick, okay, so much oil slick means does not indicate that it is natural. So that means it is the man-made, it is artificial. So this coming from the ship. So that basically indicates the pollution, oil pollution. Okay. So this is not always oil slick. Does not mean always they are petroleum exploration. In many cases, this basically the oil slick developed from the leakage from the ships. So that we need to be little careful. Now, after this remote sensing part is over, it's done, and we have prospected some of the areas, potential areas where there are potential areas of this petroleum accumulation. Then what we need to do? We need to go for seismic surveys. Seismic survey. Okay. So based on the seismic survey, we can get the subsurface geological. See here. Here you see here there are some folded structure, for example. So here are the possible areas of oil accumulation. Okay. So from seismic survey we can interpret that. Okay. Here are many such examples I have put here. So here you can interpret there are a number of faults. There are some kind of here you can see some old. Okay. So that you can interpret from the seismic data. Like here you can see this is not in India. You see here in the Gulf of Mexico, you can see here this is the folded structure is very, very prominent in the seismic data. Some of the fractures also here. Okay, basically it is a salt core anticline. Okay, so this is the areas where the possible areas of oil, petroleum accumulation or petroleum accumulation, it is a perfect area. Okay, so that from seismic data we can interpret that. Now this is one more example you can see. Here there are the folds as well as there are the faults. So this is one of the possible areas of oil accumulation. You can find this is another area of oil accumulation. So based on that we can interpret some of the, we can this narrow down the areas that where petroleum can be more precisely we can target. Okay, so seismic survey, because seismic, after remote sensing we should go for geophysical survey like gravity, and then seismic survey. And then after seismic survey is done and we can narrow down these areas that here the petroleum occurrence chance is very, very high, then we go for drilling the oil. Okay, although in my lecture this is not very important to tell about, so just to touch upon this the strategy of oil exploration, it is not ending at remote sensing. So remote sensing, then followed by geophysical observation, and particularly seismic survey, followed by drilling. But drilling is a very expensive affair. It's very costly. Drilling, there is an approximate costing here around $10,000 per meter of drilling in case of offshore rig. So you understand how much expensive it is. So before drilling, you should be very, very careful that there are oil, chances of oil, getting oil there is very, very high. Because if you miss it, if it is a dry well, then the company causes a lot of loss. Okay, so that is why you need to be very, very careful before drilling. Okay, sometimes even after drilling, oil is there, but you can recover only 40 to 50% of the oil because of its volatility, because of its weight, and because it is volatile in nature. 40 to 50% oil it generally comes out through the well, but remaining oil will not come out. So for that, to do this enhanced recovery. Enhanced recovery, what is done? This water is this steam, basically vapor, water vapor is pumped into it. When water vapor is pumped into it, what will happen? It will put pressure, then oil will come out. Okay. Now this is the system architecture for exploration. Okay, this is what ONGC follows. In this architecture, they do that remote sensing data processing input. Okay, then existing the data, geological and other kind of data, geological data analysis. Okay. So here seismic data processing is very, very important, and is the log data analysis and real-time data during drilling. Also, so all these data together we need to see together, we need to visualize together, we need to analyze together, and we need to integrate together, and based on that we need to take the decision, and whether this oil exploration, success of oil exploration is based on this, how nicely we can integrate and we can visualize different kind of information together. Now we are coming to the non-conventional hydrocarbons. So because as I told you, these conventional hydrocarbons, they are relatively easy to extract, but this volume of the non-conventional hydrocarbon is very, very less. So because this, as we already discussed, that hydrocarbons, these are not a renewable resource, it is a non-renewable. So after you extract it, then it is gone, isn't it? So the resource is limited, so we need to go for this non-conventional hydrocarbons. This is the pyramid you can see. So as you go down, the volume of the hydrocarbons is very, very large in case of non-conventional. But here what happens is for exploring or extracting oil, non-conventional hydrocarbon, it is a little expensive. It is much more expensive, and also it requires very high-end technology. So one is technological, this improvement is required, and a lot of expenses is required to extract these non-conventional hydrocarbons. In non-conventional or unconventional hydrocarbon resources, broadly these things comes like oil shale, tar sands, heavy oil, shallow basin methane, then basin centered gas, coal bed gas, or popularly known as coal bed methane or coal CBM. So now this oil shale, this is the oil resources like oil shale, and then we have tar sands and heavy oil. I am not going to elaborate each one of them. Rather, we can focus on one of the application like coal bed methane exploration, how to explore coal bed methane, both remote sensing and data usage. Okay, so in case of unconventional hydrocarbon resources, there are gas resources or gas hydrate, then there is a shallow gas, then there is a tight gas, then there is a basin centered gas. So like gas hydrate occurring at large depth, at sub-zero temperature, and under high pressure. So exploration of gas hydrate. So you need this, follow this procedure like depressurization by steam, then chemical method, and there is a national gas hydrate program is there in India that focused on targeting gas hydrate. Okay. Then shallow gas occurring at near the surface. Shallow gas can occur in paleochannel also. So mapping paleochannel is very important in some of the cases. So in paleochannel, this can be accumulated, this shallow gas. So that can be, paleochannel can be identified using radar data, because radar data related to material, this your surface cover. So this is kind of strategy we can adopt. And a tight gas, it is a natural gas occurring in tight reservoirs. So reservoirs having ultra low permeability, so less than 1 millidarcy, so are known as basically tight reservoirs. And coal bed gas or coal bed methane or CO2, it occurs in the cleats of the coal. So exploration is equally viable when their depth of occurrence is less than 300 meters. This is very important. If the depth of occurrence is 300 meters and when the permeability is high, then only this we go for this exploitation of coal bed methane or coal bed gas. And basin centered gas, unlike conventional hydrocarbons, it lacks down deep water. So below this there is no water, and the spatial coverage tends to hundreds of square kilometer. Porosity of the material is like this, and its permeability is little less here. Okay, so these are the gas resources. Okay, so now coming to the coal bed gas or coal bed methane. So coal bed methane, like natural gas generated in the formation of coal through coalification process of vegetal matter. So this gas is absorbed in the coal, in the cleats of the coal. So this is basically coal bed gas. So during the formation of the coal itself from the vegetal matter, these gases are formed and these gases are absorbed in the cleats of the coal. This is known as coal bed gas. Okay. So now in coal bed gas there may be methane compositionally, there may be methane, there may be ethane, there may be this thing your ethylene, propylene or propane, butane. There may be also carbon dioxide, nitrogen, oxygen, helium, hydrogen also. So when this in this coal bed gas methane percentage is very high, okay, and more than 80%, okay. When this is known as coal bed methane, when methane percentage is very high, more than 80%. So as I already told you, this coal bed methane occurs in the cleats of the coal. It can occur as in situ gas inside the coal. It is absorbed. So it needs to be for releasing this, you need to depressurize, you need to heat it, then only the gas will come out. So there are procedures are there, and sometimes it may be accumulated in the fractures. So in the fractures itself, between the in coal formation, this coal bed methane can occur as a free gas. Okay. Now there are the certain factors which control the in situ this gas formation and accumulation. So the accumulation and formation of this situ gas, these factors like age of the formation. What is the age of the formation? What is the coal reserve? How much coal is there in this deposit? Thickness of the coal seams, that is important. If thicker coal seams, you will have more probability of having more coal bed gas. Then quality of the coal in terms of the petrographic composition, okay, and the grade of the coal. Okay, so if the grade of the coal is high, then this coal bed gas content will be high, and the presence of cleats, that is also very important. So, and absorption properties, how much it absorbed, not absorbed, adsorbed, how much it is absorbed, that is very important. And petrophysical properties of coal seam, hydrogeological condition of this formation, what is the hydrogeological condition, and potential for hydraulic fracturing of the coal seam. So these are the factors which control that. So we have used some of these factors for prospecting of coal bed gas or coal bed methane. And in case of free gas accumulation, what is important? The factors important are geological structures mostly the lineaments and fractures. And important is whether the lineaments or fractures these are there in the propagated from the basement to some intermediate depth, or when it is propagated to the surface itself, then it may come out also, the free gas may not be available. So that is very, very important. The permeability of the overlying strata is important, thickness of the overburden, that is important, because for exploring, your thickness should not be very, very large, and this the material above this should be impermeable so that this coal bed gas cannot come out. And this, what is the compressive strength of the overlapping strata, what is the permeability of the coal, and in situ stress in coal seam and fluid pressure. So these are the parameters which controls the this adsorption of the coals, and so that the coal will coal bed gas, adsorption of the coal bed gas, and so that coal bed gas will be released and it will be there occurring as free coal bed gas. Now there are the parameters what we have used for in situ gas prospecting. Okay, these parameters like thickness of the coal seam, ash concentration in coal, density of coal, moisture content in coal, fixed carbon content, volatile matter, and depth of coal seam. So these are the parameters we have used, that we have got from the these mining agencies. Basically, we have worked for in one of the area of Bharat Coking Coal Limited under Coal India Limited in Jharia Coalfield. So these data we have collected from the litholog and from the from the your mineralogy and this your quality of the coal. Now this the parameters what we have used for free gas prospecting, like geological structure, like synclinal and anticlinal fold axis, this faults and faults, intersection of faults and structures, faults and fractures. So this we have gone for that. What are the geological structure occurring? What is the overburden thickness, and what is the thickness of the coal seams? This is the geological your parameters we have used. This structure like syncline, anticline, faults and fractures, intersection of faults and fractures, overburden thickness, and thickness of coal seams. Okay, and propagation of basement faults to the surface, that we have studied. If this is propagated to the surface, then this gas will come out. So that is, free gas will not be available, only in situ gas will be available. So in that case, we can estimate only the in situ gas content, coal bed gas content, and thermal anomaly due to igneous incident, and what is the geothermal gradient, or if there is any thermal anomaly due to coal fire, subsurface coal fire or not. So geothermal gradient, geothermal heat, thermal anomaly due to coal fire, okay, and thermal anomaly due to igneous intrusion. If something is there, so those things will be acting as the parameters for free gas prospecting, because in this case the gas will be released from the coal seam and it will occur in the fractures. Okay. And underground mine galleries, if there are open spaces are available, this is when the mining is done by board and pillar method. So if there are underground mine galleries are available, open spaces are available, then this free coal bed gas can be accumulated. Okay. So now based on these parameters, we have studied one of this block, Parbatpur block of this coalfield, Jharia coalfield, and for this block there are other block as well. We have used all those parameters that basically this courtesy to Bharat Coking Coal Limited. We have got lot of litholog data. Okay, only the remote sensing based observation we have made ourselves, like geological structures and geology of this area we have collected from the published maps, and litholog we have collected from them, and this grade of the coal and different parameters related to coal that we have collected from the mining agency Bharat Coking Coal Limited. Using all those parameters together, I am not going to the details how we have estimated this coal bed gas free and in situ. Basically, we have estimated in situ gas content, and followed by that we have prospected the areas of this free gas content all over the coal field. That we have done based on the remote sensing data and geological data. Finally, what we see, this is this Parbatpur block. If we see, that is this coal bed gas content in meter cube. Coal bed gas content would be available, and maximum available coal bed gas is somewhere. These are the areas. So we can prospect these are the areas. In fact, there are the extraction of coal bed gas is taking place in many of the areas by many agencies in Jharia coalfield area. So this is all about this your lecture presentation.